Hello and welcome back to e-sipnayan. For today's video, we are going to solve rational inequalities. The objective for this video are distinguish irrational inequalities and solve rational inequalities. Let's define first what is a rational inequality. It is basically composed of rational expressions combined with the inequality symbols. We have greater than, less than, greater than or equal, or less than or equal. If we compare it to a rational equality, the only thing that differs is the symbol used. So for rational equality, we use equality symbols, whereas for rational inequality, we use inequality symbols. So please familiarize yourselves with the symbols being used for rational inequality. Some examples are 1 over x is less than or equal to 7, x plus 2 over x minus 3 is less than or equal to 0, and lastly 1/2 plus 2 over x squared minus 4x minus 5 greater than or equal to 0 are all examples of rational inequality. Moving on, let's now discuss how to solve rational inequalities. Now, here are some steps we can follow in solving rational inequalities. First, get the meaningful values for the numerator and the denominator. What are meaningful values? It says here that meaningful values are values of x in the numerator and the denominator when the expressions are equated to 0. Next, test the meaningful values. Third, create the number line interval using the meaningful values. Fourth, test a value per interval. And lastly, write your answer in set builder notation. These are the steps to follow in solving rational inequality. It will be a very long process. It will require a lot of solutions, and we will be following all of these 5 steps. For example number 1, we have x plus 2 all over x minus 3 less than or equal to 0. To start with the first step, we need to get the meaningful values. Again, for the meaningful values, we simply need to solve for the x, each for the numerator and the denominator. So let's have our solution on this part of the slide. These are the meaningful values. So let's have the numerator first, then the denominator. So for the numerator, the expressions given are x plus 2. We need to first equate it to 0, then solve for x. Solve for x after equating the numerator to 0. So what we need to do here is to simply transpose 2 to the right-hand side of the equation. And so the value of x is equal to simply negative 2. This is one meaningful value from the inequality. Meanwhile, for the denominator, we will be doing the same thing. We'll get the expressions below. The expression below, which is x minus 3, we equate it to 0. Then, the same thing as what we did earlier, we need to solve for x. Now, we need to transpose negative 3 to the right-hand side of the equation. And so, the final value of x is equal to positive 3. Another meaningful value is x equals 3. Now, what is the essence of these meaningful values? These meaningful values are possible solutions to the inequality. And how do we check if they are indeed solutions to the inequality? We're done with step 1. The meaningful values are negative 2 and positive 3. Let's now proceed with step 2, where we test the meaningful values. So how do we test the meaningful values? We just need to check or substitute the values of x back to the inequality and see if the inequality is being satisfied. Let's start with x equals negative 2. So if x is negative 2, the inequality becomes negative 2 plus 2 all over. For the denominator, that becomes negative 2 minus 3. We are checking if it is really less than or equal to 0. Let's put a question mark here. Now, simplifying further, if you input this whole expression on your calculators, you'll get 0 over negative 5. And 0 over negative 5 will simply give you 0, which is may not be less than 0, but it is equal 0. So this means that x equals -2 is a really meaningful value, and it is a solution to the inequality. So this is the first one. How about the other meaningful value, which is negative or +3 rather? So we have here, substituting value of 3, we'll get 3 plus 2 in the numerator. In the denominator, we'll get 3 minus 3, which is less than or equal to 0. Again, we are checking if the inequality will be satisfied. Now, if we simplify this further, the numerator becomes 5, denominator is 0, and any fraction or rational expression whose denominator is 0 becomes undefined. So, the inequality is not satisfied because this becomes undefined. And so, what will be our conclusion? X equals 3 is not a solution. So that's how you perform steps 1 and 2. Now that we were able to obtain the value of the meaningful values in step 2 and check which among them is a solution or not, we now proceed to step 3, where we create the number line interval using the meaningful values. Unlike in a rational equality wherein there are specific values of x that will serve as solution, in a rational inequality, we do not really have specific values. Rather, we have a set of values or intervals. So how are we going to use the meaningful values to create intervals? That is for step 3. So recall that -2 is a solution, 3 is not a solution, and if we draw this in a number line, we know that given an inequality, if a value is a solution, we draw it or graph it as a shaded circle. Whereas if it is not a solution, then it is an unshaded circle. To be able to know the intervals, we will be drawing now a number line and plot the meaningful values, -2 and 3. So -2 will be found to the left of 3 simply because that is the nature of the number line. Everything that's less than will be plotted to the left. So this is x equals -2, whereas the unshaded circle is the value of x where it is equal to 3. This will serve now as our border line. I will make now the borders here, and this will serve our interval. Since we have two meaningful values, that means we are going to have two borders, and that will give us 3 different sections of the number line. So let's talk about this area first. The values of x to the left of this value x equals -2 are numbers like -3, -4, -5, and so on until -infinity. Or basically, this set of values to the left of -2 are values of x that are less than -2. Meanwhile, on the middle portion, this will be values in between -2 and 3. So we can say we have here -1, 0, 1, and 2. And of course, numbers in between these intervals. Now, if we write it into notation, we have the value of x, which is greater than -2, but less than 3. In terms of the inequality symbol, take note that this is a shaded circle. So we have here x greater than or equal to -2. Then, this will stay as less than because 3 is not included. So for the middle portion, we write it as x greater than or equal to -2 but less than 3. And for the last section, this will be values such as 4, 5, 6, and so on until +infinity. And so this section will be encompassing values of x that are greater than 3. So these are now the intervals that we have. We are done with step 3. For step 4, we will now test a value per interval. So to check and to know which among these 3 are values or solutions to the rational inequality, we will be choosing a value from the interval, substitute it to the inequality, and see if it will be satisfied. So for the testing part, for the first part, we need to select a value of x less than -2. So I can just select -3. Then I'll substitute it to the inequality. So I'll test x equals -3 and see if it will satisfy the inequality. Substituting the value, we have -3 plus 2 all over -3 minus 3. Is it less than or equal to 0? Okay, so simplifying further, the numerator will be having here -1 all over -3 minus 3 is -6, which will be less than or equal to 0. Again, let me rewrite that. That's less than or equal to 0. Simplifying this further, the negative signs will be cancelled, and so we'll have here 1 over 6 less than or equal to 0. And we know that positive numbers are greater than 0. Therefore, this is not satisfied. And so, these values, x less than -2, are not solutions to the inequality. So we're done testing the first interval. We still have 2 more to test. Moving on, for the middle interval, these are values in between -2 and 3, including -2. But since we already checked that -2 is a solution and 3 is not, we will choose values in between. So let's say I want to choose x as 0. Now let's substitute. That becomes 0 plus 2 all over 0 minus 3. Is it really less than or equal to 0? Simplifying further, we'll have 2 over -3, and any negative value is indeed less than 0. So this means the inequality is satisfied, and therefore this interval is a solution to the inequality. And for the last section, we need to test values greater than 3. So let's select values greater than 3. A value greater than 3 could be 4. Substituting it to the inequality, we have 4 plus 2 over 4 minus 3. Is it really less than or equal to 0? For the numerator, that becomes 6. Denominator becomes 1. So let's check if it is less than or equal to 0. Simplifying this further, we have 6 less than or equal to 0, and 6 is a positive number. Very obvious that it's not less than 0, and so this is also not an inequality. And that means the last interval is not a solution to the rational inequality. That leaves us of x equals -2 and this range of values where x is greater than or equal to -2 but less than 3. So therefore, for the final answer, let's write it in violet. The solution to the inequality is this interval, x is greater than, including -2, but less than 3, not including 3. So this is now our final answer. On to the second example, we have 2x minus 5 over x minus 5 less than or equal to 3. We again start by getting the meaningful values. I will just write here mv. For the numerator, what we have here is 2x minus 5. We will be equating it to 0. Then solve for x. So we need to isolate x. Let's transpose 5 to the other side. We'll now have 2x equals positive 5. Then divide both sides by 2. And so we'll cancel this. The first value of x will now be equal to 5 over 2, which is simply 2.5. For the denominator, we have x minus 5. This one is quite easy to solve. And so the value of x here, simply transpose -5 to the other side, will get 5. So the two meaningful values we have for this example number 2 are x equals 5 and x equals 2.5. Moving on to step 2, we need now to test the meaningful values. So when x is equal to 2.5, we substitute it to the expression, rational expression on the left hand side. That becomes 2 times 2.5 minus 5 all over 2.5 minus 5. Is it really less than or equal to 3? Now, we need to simplify. This becomes 2 times 2.5, that's 5, minus 5, it becomes 0. And on the denominator, that becomes negative 2.5. So, this form will simply be equated to 0. And we know that indeed, 0 is less than 3. So, that means x equals 2.5 is a solution because the inequality was satisfied. How about for the other value? The other value of x is 5. We now again substitute to the rational expression. So that will give us 2 times 5 minus 5 over 5 minus 5. That's less than or equal to 3. We're very certain that the denominator becomes 0. But let's just show it here. That's 10 minus 5. That becomes 5 over 0. And that is not really less than and not also equal to 3 because this is undefined. And that will give us a conclusion that x equals 5 is not a solution. Now that we were able to get the meaningful values, 2.5 and 5, we will now proceed to steps 3 to 5. We'll be creating now the intervals. Now, similar to what we did earlier, or for the first example, if we were able to identify that the meaningful value is a solution, we graph it as shaded circle, if not an unshaded circle. So we will now draw the number line, plot the points. Basically, 2.5 will be plotted to the left of 5 because it's a lesser value. So x equals 2.5 is here, and the one to its right is x equals 5. Now, to make the interval, since we have two meaningful values, that means we'll draw two border lines, and that will give us a total of 3 sections of the number line. Similar to what we did earlier, we will now construct the set of values per interval. Now, values to the left of 2.5 are as follows. We have 2.4, we have 2.3, and so on. So that will simply imply that the values to the left of 2.5 are values of x that are less than 2.5. Meanwhile, in the middle, it will be again an interval of two values. So x will be greater than the value of 2.5, but we will include it since this is a shaded circle. Then, for this part, the value of x must be less than 5. And since it is an unshaded circle, we use less than. So this is the interval in between. And lastly, the values to the right of 5 are 6, 7, 8, 9, and so on until positive infinity. So this means this interval will encompass values of x greater than 5. So these are now the intervals. Lastly, we will be testing the values. So for the values, we'll select or do it rather one at a time. For the first section, let's get a value of x that is less than 2.5. It can be decimal, it can be a whole number, so I'll just have 0 so that I will not deal with any decimal. It can be any number anyway, less than 0. So substituting the value, that gives us 2 times 0 minus 5 all over 0 minus 5. Is it less than or equal to 3? So for the numerator, that becomes 0 minus 5. That's negative 5. For the denominator, that's also negative 5. Less than or equal to 3. This will give you positive 1. And it is indeed less than or equal to 3. And so, this means that this interval will satisfy the inequality and is a solution to the inequality. Moving on, let's now have a test value for the middle interval. So we just need a value in between 2.5 and 5. And so I am thinking again of a whole number. Let's have 3 instead. So let's substitute. We have 2 times 3 minus 5 all over 3 minus 5. Is it really less than or equal to 3? Simplifying further, we have 2 times 3, 6 minus 1. 6 minus 5 rather, that is equal to 1. And then for the denominator, that is 3 minus 5. That will give you negative 2. And it's true that negative 1/2 is less than or equal to 3. So we were now able to confirm that negative 1/2 is less than or equal to 3. And that means this interval is also a solution to the inequality. And last but not the least, let's test a value from this interval. Let's have x equal to 6. And then let's substitute. So we have 2 times 6 minus 5 divided by 6 minus 5. Is it less than or equal to 3? For the numerator, that's 12 minus 5, which will give us 7 over 1, or simply 7. Is 7 less than or equal to 3? Definitely this is very wrong. And so the last interval is not a solution. So how will we write now the solution to the inequality? So we can have values, this interval and this interval. Let's just combine them in one set builder notation. So we can say that x can be less than 2.5 and it can be in between x greater than or equal to 2.5 but less than 5. And this is now the solution in set builder notation. And we are done.